Okay, so you should have these elements already dragged into your Simulink window. Alright, so we're going to define each one of these solids. We're going to turn these solids into a linkage. The fourth one here will be this virtual link L4, which ties back the link 1 to this base here. Alright, so before we do this, we need to define some parameters. We need to define what is L1, L2, etc. So for that, we'll go to the script file. So in the script file here, what I did, I just copied the parameter that we had before, L1 to 4, right? Keep it as millimeters, right? And now what we want to do is we want to define a speed at which it will rotate at, right? So we say theta 1 or theta dot for the length. For link 1 is 1 radians per second. We want to go from initial of 0 to we want to finish off at theta f is 180 degrees. Well, we convert it to radians here, right? And we want the simulation to run for 2 seconds. So the time final is 2. So we create a vector from 0 to 2 seconds in increments of 0.1. So this will create a t vector 0, 0.01, 0.02, 0.03, etc. all the way to 2 seconds, right? The next now is we want the angle or the trajectory of the joint. That's what we call it, right? The joint trajectory. In this case here, it is the angle versus time, right? So the angle would be, well, speed by time. Remember, velocity is distance over time, so distance is velocity by time. So we multiply theta dot by the time here, and then that value now we put it in the vector with t. So this is what we need to specify in Simulink or in Simscape. So this is what drives the joint, the first joint. Okay, so with that Simulink file, sorry, that script file, I should say, defined, now we have, and if we click run, L1, L2, L3, L4 would be stored in the workspace. So now we could actually use those values to define our solids here. So to define our solids, we can go and double click. So this window would pop up. Now, right now it's a cube because it's 1 by 1 by 1. Right, so we want to change our units to millimeters. Right, and we want it to be elongated in the x direction. So we want it to be L1. So we type here L1 in the x direction. And then what we could do, we could press, well, let's say they press F5. So we can press F5 to visualize it. Right, so we can click OK, just to come out of it, go back into it, just so we could see it. So now it looks more like the linkage. Right, the next thing we want to do is we want to create points at which we could connect the joints. So for that, we go to frames and we click on a new frame. So right now we have a frame in the center, right? But we want it on the end. So what we could do is that we could rotate, just click on the mouse wheel, just like you would in SolidWorks, and click on this back face here. And then you click based on geometric feature, use selected feature. So what we did there is that we are creating a frame on the body, right? By doing that, by defining the frame origin, and we want the origin to be on that selected figure, which is what we selected and it's on the middle. So we have one frame there. Then we can click save. So we see that frame is named frame 1, right? So that is at the bottom of the frame. What we can do is that we can add another frame. So we go and click the plus here, and we want another frame on the end here because now this is where you would connect the L2. So we go to the same process, we click on it, the face, use selected figure. So we have a frame attached to that end. So now we can click save. So when you click apply and OK, you would see here now the solid has now F1 and F2. You can actually drag and open this a little bigger. Alright, so you could have F1 and F2. So now F1, we could connect it to the world, quote unquote, world being the world frame or the base. And we can also connect that to the revolute joint stemming from link 3. Right? But when we reach to that end, we will do that. So now we could, what we could do, we could draw a line, just hold on the mouse wheel and connect all these 3 over here. Right? So what we have done, we had set up the configuration, we are define the world frame and mechanism configuration. Right, so what this is as it means configure the mechanism. So right now the gravity is set at 0, 0, 0, 0. Right, now if it is we want to include gravity later on, we can set it to be in the y direction, for example. So that means in the y direction you could have negative g, negative 9.81 here. Right, but for now you keep it at 0 because it's just a planar mechanism. Right, so that is the first step. The next step now is to actually connect a joint to link 2. Right, so what we will do, we will define link 2. So we could drag this around here. Right, so we go to the same process, millimeters, call this L2. We go onto frames. Right, we need to press F5 to update. Go into frame. Right, so we need to zoom out. So instead of zooming out all this way, we will just come out of it. So it will update, right? Right, so that is the second frame. Right, so I'm going to repeat this for you. Repeat this for the other two linkages. Right, so all solids were updated with the respective lengths and the frames. Right, so one thing to note here is that you notice we haven't put in any mass properties. And that's because under inertia here, Simulink will automatically calculate the values of second mass moment of inertia. Right, so right now it is assuming a density of 1,000 kilogram per meter cube. We are just interested right now in the kinematics of it, so we are not concerned about the mass. Right, but next week what we will do is we will include mass in the script file so that we could include, it will consider the mass then. Because that's how we need to calculate the torques, right? Okay, so now that we have the masses, now we need to join them. Right, so if you notice here now, we have link 1 is connected to link 2 with a revolute joint. So that will be this joint here. Right, you could also just come here and label link 1, link 2. Right, so we can have a nice label for each one. Right, so you will notice on your link here you have B and you have F. Right, B and F. So one is the base and the other one is the follower. So the base being the link that is coming from, and the follower be the link that is, well, following. Right, so to connect it, we simply just draw a line from base to follower. Well, from F2. Remember F2 was the frame that is on the other end, and then follower. So this will go to the frame on this end. So this will go to F1. Right? And now I could do the same for each one here now. Right? So from 3 to 4, let's drag this across here. Yeah, so from 3 to 4, we said that 4 is a virtual link. So we have 3 connected to 4, which is that fixed link here. Right? Now 4 is also connected to 1. So our base would be connected to the extreme end of L3. And now this now will link back to link 1, right? So this will actually come and join to this line here, right? Remember, this was the line that we started from, right? So what we have here now is our forward mechanism, right? So with it finished, more or less here, we have the general layout. You could click run. This is so it, right? So when you click run, it will, and you open the workspace, or you open your Matlab window, I should say, you would see this here, right? Now, what I did, I actually came in here, double click mechanism, I actually put a gravity here as minus 9.81. Right, so when I clicked run, you would see that the gravity is having some type of effect here, right? Now, more so, I wanted to see the orientation of it, link 4, link 3, etc. Now, if it is your diagram is not looking like this, for example, L4 is a bit too short, right? What it could be is that when we did the parameters, you probably, I think I entered the wrong parameters here. So you can actually put in the parameters from the script in here. Right, so L1 supposed to be 6.75. Right, and then you run this again. Right, wait till it, right, and then you come back to the window here and you click run again here. Okay, so when you go onto your MATLAB workspace window, you would see, so you're supposed to see an updated. Now you could rotate this around just like you were doing SolidWorks. You could right click, fit the view, right click, you could have your standard views. So you could have your top view, right? It's not as graceful as SolidWorks, but you can actually click on your links here and let's ensure that. So you see the orientation is a bit off in this case here. So it's a challenge really to get it to look like how we want it to look in the diagram. So this is how it is in the diagram. L4 on the bottom, L2, well, L1, L2, L3, and L4. Okay, so now we could continue in this diagram here to update and actually actuate the joint, make the joint actually rotate. So I will just come back in here and remove the gravity for now. Oops, it did not remove. Right. Right, so now we want to actuate the joint. Right, so we normally would put our motor by our joint. So in this case here, we double click revolute joint, and you will see this window. Right, so the primitive is RZ, meaning that is rotating about the Z direction. Right, you could actually come here and specify a target velocity. So you could specify an actual angular velocity here, but we don't want that. We want to use what we had specified in the script file. Right, so for that, we could have torque automatically computed, motion provided by input. So that means now we're going to provide our input. Now when we do that, you would notice something here when we were to close this off. You would see that the revolute joint has a queue here, meaning that now we have a port here that is ready to accept an input. Right, so the input is coming from this theta vector here. Right, so we need a way to get this into our Simulink file. Now remember, this is actually stored, that theta file is actually stored in your workspace. Right, so on your library browser, you could come, scroll up to the beginning here and look under Simulink, you look for sources. So you can click on sources, and what we are looking for is from workspace. Right, so we want to take a value or a vector from workspace. So we would drag this across, here. And then we could double click it to open it up. And what is the data we are looking for? Well, the name of that vector was theta, if we could recall. All right, and apply. Okay. All right, so whatever it is in that vector in the workspace will come into here. Now, ideally, it would be nice to just connect this over here, and it used to be like that. Right, but now this here is a simulation or a mathematical variable, and what we have in these lines here, a physical variable. So we need a simulink to physical space converter. So for that, we would scroll back down to our Simscape. Right, so we need to look for that simulink to PS converter. Right, so under utilities here, you would see simulink to PS converter. PS meaning physical signal. Right, so we could drag that across here. Right, so now we could connect this. Right, so that's the Simulink source on your workspace, and then this will now be a physical source. Right, now we have specified theta versus time. Right, so what we need to do is double click this here, if we could, right, and we want to go to input handling, and you want to put filter input derivatives calculated. Right, so we want to select second order filtering, so it will differentiate it twice. So you will get your velocity and then you'll get acceleration from that signal. And then you click apply, OK. So what that will do now, that will actually drive the joint. Right, so what we could do now, we could actually click run here and have a look at the Matlab window. Right, so this is the Matlab window. You can click on link 1 just to get a reference, and you can click play and you would see it here now being actuated like that. Now, the simulation is only running for 2 seconds, so it may not reach the full 180 degrees that we had specified. Right, now it is a bit hard to follow here, but what we are seeing here is that L1 is remaining fixed. We have L1 highlighted, and everything else is rotating. But in reality, L4 is the one that's supposed to remain fixed. Right? So it means that something is not right with the model. Right? So that here is L4. Right? So we need to revisit the model now. And what we are seeing here is that we have the base, the configuration, etc. attached to link 1. So what that is doing, that is fixing link 1. So what we could do is we can remove this link here and actually send that to link 4 instead. Now to do that, how did I do that? I right clicked on the line and I will drag out this red dot line and then let it join onto the F1, that line there. So what I have done here now is actually grounded the link 4. So we could click run again, and you could see now in this window here now is updated. So we have link 4 is the one that is grounded. Right, link 1, well, we need to just rotate this here. Right, so we have link 1 that is rotating, that is highlighted here for 2 seconds. Right, so now we can go on now to actually pull in from this now some actual graphs. So that is what we will do now. To get values of torque and all that, we could click on the joint. Right, so you would see it have a number of items here for sensing. So we want to detect angular position, and we want to detect the actuator torque. Because we say that if we are putting a motor here, we want to know what is the torque the motor is, what torque the motor would have to produce to give us the required motion. Right, so when you do that now, you will notice that we have two more ports open up here. Q being position, T being torque. Right, so these are physical signals that we must now convert to Simulink signals. Right, so for that we need a physical signal to Simulink signal converter. So we go to the library browser and we need a physical signal. So it's basically the opposite of the one we had used previously. Right, so we could drag that across here. Right, so you could actually copy Control C and V, that's a copy signals. Right, so you can actually connect that like that here, connect that to that here. Right, so now that we have those signals, we need to go to something to be where we can see the information. So that will be a scope. Right, so we need a scope, so we come back here and we look for sinks. Sinks meaning that we're drawing data. Right, so we could go to this scope here and we could actually drag it across. Right, and we could call this angular position. And again, we could copy and paste the scope. Call this torque. And now we could actually connect that there. Alright, so we could actually now just click run on this here. So every time you run over, so the information will go towards it. So on the angular position, you could double click it. And you would see how the angle increased over time. So we went from 0 to 2 seconds, and this is the angle in radians. Right, remember it was a constant velocity, so it was linear. In terms of torque, this would be the torque. So you could see the torque is very small because this is a planar mechanism. Right, remember we did not specify any profile. Ideally, you would want to specify a joint trajectory that is not jerky. So for example, it would start off smooth, reach a peak velocity, and return to rest very smoothly. Right, and those are things you could experiment with later on. Alright, so if you want to zoom in on this, you could actually just click the zoom button, and you could actually zoom in and see how small the actual value is. Now, if you want to get back to the main screen, you click down arrow, like that here. When you zoom back in, you can just highlight a block, and so you could see it oscillating around. So a very small value, between 0.5 thereabouts by 10 to the minus 9 Newton meter. Right now, the reason why we're getting this spike here is because we are kind of breaking the laws of physics in that we are instantly accelerating it. Right, so again. Right, so we can have a look at, I'll just rotate this around just to be consistent with what we have in the diagram. Right, so if you notice, if you could recall, we had specified theta to be 0 degrees in the beginning, right? But if you look at this entire process, it does not start at 0 degrees, right? This is the start point here, right? Which indicates that something is not right with the model, right? So this is all sanity checks that you need to, make sure everything is making sense. But what we do notice is that at time is 0, the link between links 1 and 2, that joint there, this is actually 0 degrees. So it means that we are actuating the wrong joint in that case. Right? The motor, we are saying the motor is actually here between joints 1 and 2. Right? So if we revisit back the model here now, we could recall that this is link 1, this is link 2, and the joint in between. So we really are in fact actuating the wrong joint. Right? Ideally, we want to actuate between links 1 and links 4. I remember link 4 was the solid, was the fixed frame, or the fixed link. Right, so that is a change that you could make now to ensure that we are true to what we want to analyze. So this here is the fixed version. Um, what I did is last joint, we say that is what we actuating. Right, so this here joint represents this connection here. Right, so you go back to joint 1. What you need to do is we are not no longer specifying motion, so it's automatically computed. For torque, we do not need to calculate torque, so we keep that to none because there's no actuation happening there, right? And for sensing, we need to remove actuator torque because again, there's no actuation taking place. So all we want to do is measure position. Okay, and for revolute joint 3 will then, just as before, automatically computed provided by input. Right, you could go on after and put your sensing ports and all that if you wish. Right, so when this is run, you could have a look here at the output and you could see now link 1. Right, you could see link 1 is at 0 degrees to link 2 at the beginning. Sorry, 0 degrees to link 4 at the beginning, which is what we wanted. Right, so in terms of the direction, well, you could go ahead afterwards and change your signs. So theta can now be negative if you wanted to start from the opposite end, for example. Right, so now that we have everything, we could actually manipulate the values to get the motion we want. So the reason why we are doing all this is that we're able to obtain that actuation torque. So that we will know if the motor is capable of providing the motion that we want.